Okay, so today we're getting into one of our first lectures on some actual gameplay programming and physics. So this is on collision detection and collision resolution in general, like what that problem means. And then we will talk about axis-aligned bounding boxes. So if you've never heard of that before, don't worry, it's very simple. It's just rectangles. That's all that means. So, collisions in games. Most games have things that collide in order to make some sort of game mechanic. Again, this course is not a game design course, so we're not going to tell you if something is a good mechanic, but we're in the position that our boss or designer of the game has told us to do something, and now we have to do it, right? So this is game programming. So how would we do collisions in games? So collisions programming involves two main stages to that problem. One is called collision detection. So given two things that are moving with some given shape or bounds, determine if they intersect. So are these two things currently intersecting? And detection is a geometric problem. You're typically going to be working with shapes represented in some form and then doing the math that involves detecting if those things are overlapping in whatever space they happen to be living in. And next, after you've detected collisions, you may want to resolve those collisions. So given that two entities have collided, of course, if there's no collision, you probably don't have to do anything. But if there was a collision, determine what to do to resolve the physics of that simulation, right? So in the real world, collision resolution is just like the physics of the world. My hands can't really overlap. But in the game world, they can very easily overlap. And if you want that to look intuitively like decent physics, then you would have to do something to resolve the fact that the game is in this state that you don't want it to be in, right? So two things are overlapping. What do we do? So some assumptions for these slides. We'll be using the course definition of entity, and that's going forward with the course. That's what we mean whenever we say entity. And we are going to assume that entities have the following properties. So they're going to have some position, x, y. If they are moving around, then they have some velocity, which is the delta x and the delta y, so just a change in x and y on every frame. And then they're going to have some sort of bounding shape. And for our course, we're going to be dealing with circles in assignment 2. We have rectangles and lines for the rest of the course. So some sort of shape that determines the boundaries of that. I had a question once that was, is a bounding shape, is that the same as a hitbox? Basically. Okay, so hitbox is just a name for the box that gets hit, which is essentially the bounding shape of an object. So our goal is to learn the mathematics that allows these entities to hit each other and interact in our game. And of course, we're only talking about the 2D case, because if we had to talk about arbitrary 3D volumes in this course, that's all we would be talking about. It would take too long. And of course, the answer to this question here, how do we detect and resolve collisions? If you were using a game engine like Unity or Unreal, there'd be like a function that you call and it does it for you. But this is computer science. We don't just want to call a function, right? So in an actual, quote-unquote, actual game engine, there might be something that looks like a rigid body. So rigid body physics, rigid meaning that these things are not elastic. If they collide, then these two things shouldn't be able to overlap. So in any modern game engine, you would take an object, and if you gave it a rigid body of a specific geometry, then the game engine would have some sort of physics that resolves that for you. But for the 2D case, we're going to look at some of that in this lecture. But we don't need to build an arbitrary physics simulator for this course. In fact, there are simulators for that. Like for example, there's Box2D. So Box2D is a 2D physics simulator. And you could plug that into our game engine and have it work if you wanted to. But again, we're not doing that. I'm just going over what we would do to make a simple 2D game in this course. So collision detection problems. One of the problems would be given two entities, which have a speed, or velocity in our case, position, and bounding shape, determine if they will collide, when they will collide, or where they will collide. or maybe all three. So that is one problem. It's if you have these two things with these properties, will they collide in the future? That is one problem that we will not be doing in this course, and it's not the way that the majority of physics programming is done. It's more of, given two entities which have a speed, position, and bounding shape, the answer to this question would be, okay, maybe they will collide here. In this course, we're not going that far with it. We're just going to say, given two entities which have a current position, do they intersect? And if they intersect, then do something with it. So we're not doing this case where we have to figure out in the future where they might collide. That is useful in some cases, but not in our simple games. So we're going to be doing things like this. If we have two entities on this frame, do they collide? And later we'll talk about if they're colliding, what do we do to resolve that situation? So for example here, we have these, this blue and red rectangle. They are intersecting. The green circle and the red rectangle are intersecting, and the purple circle is not intersecting with anything else. So the result of our algorithm would have to be able to say something like that. Another question is not only do they intersect, but by how much do they intersect? Because that's going to be one of the key factors in how we actually resolve this, right? Is, okay, if they intersect by this much, maybe I need to do at least that much to resolve that thing. So for example, here we have this blue rectangle and this red rectangle, and then if we calculate by how much would they intersect, we get this other rectangle, right? And so that has a width and a height, and we'll talk about that a bit later. But first, let's talk about how we get those bounding shapes themselves. So in the real world, objects have arbitrary shapes and interaction surfaces, right? So I mean, my hand, if you shot something or threw a small thing at me and it like went through my fingers, it wouldn't actually touch me, right? But you can think of how complex it is to actually represent a shape like that in a video game. We are not going to be going that detailed with it, but if you were making like a competitive first-person shooter game like Counter-Strike Go, you would want the bullet to be able to like pass through the arm and the body, right? Not necessarily the fingers or the hair follicles or whatever, but you probably want to be able to shoot through the legs, right? Or shoot between the arm and the body or whatever. So there are completely arbitrary surfaces that you could do the math to interact with, but these are difficult to store, compute, and simulate accurately and efficiently, right? So I'm not going to be going into that detailed in this course because, again, that's what the entire course would become about, right? We're trying to get multiple different basic things in this class rather than just one thing really, really deep. So all primitive shapes in computer simulations must be made of primitive types. So, for example, in the 2D case, we can have lines, triangles, circles, rectangles. In the 3D case, we could have spheres, planes, cylinders, prisms. And so you may have heard of a poly count or a polygon count in a game. So pretty much every modern 3D game is made up of polygons, right? So if you were to simulate me in a game, you don't have that infinite precision of like the molecule level, right? So you would, wherever there's sort of a flat surface, like my face, you might have a couple of polygons there, and then some polygons for the back. You know, if you look back at the PlayStation 1 days, then a person might be like, 50 polygons, but now, of course, they're like 1 million polygons, right? So you would simulate a complex structure by having multiple less complex structures. But in this course, we're going to talk about just a simple bounding shape concept. So we are going to simulate the interaction bounds of a complex shape with a simpler one. So for example, let's say in our game, like assignment 2, we have an octagon. Well, you can think about having to detect if an octagon truly interacts with something else. Well, you've got to detect if each of its sides collide with each of the other sides, or maybe each of the points, do they lie within another polygon, etc., etc. Or you can think of Mega Man over here running. Maybe we have to like check every pixel of Mega Man to see if every pixel of Mega Man interacts with every pixel of the other thing. Well, that's a lot of work. So let's just simplify this process by having an approximation for a bounding box. So for example, in assignment 2, you're just treating octagons as circles, And you know what? That's good enough for that game. No one's going to write in to the game studio and say, hey, I detected 2 pixels where the bullet should have fired. I didn't get the world record. You know, like, whatever. Try again next time. And over here, yes, we are doing a gross oversimplification of Mega Man, where maybe if we use this bounding box for Mega Man, then if a bullet hit like right here, we would determine that as a collision with Mega Man, right? So we'll see how a couple of games deal with that, but essentially the point here is that we're taking an arbitrarily complex shape and saying, okay, that's either going to be a circle or a rectangle for our purposes in our game. So the simplest 2D bounding shape to store and compute is a circle with a given radius, right? So we're looking at that in assignment 2. We've already covered that, so I don't need to go over it again. But basically, we just have a point and we have a radius. You can't get much simpler than that. I guess a point would be simpler, but that's almost 0-dimensional, not 2-dimensional, right? So other 2D bounding shapes can be constructed with a number of line segments. So if we think we can make pretty much any geometric shape by having a bunch of line segments. And the simplest of those is a rectangle. So that's why we call this a bounding box or a bounding rectangle. How do we determine the bounding box size? So most 2D games use rectangular sprite graphics. And so images in computers are typically stored as 2-dimensional structures of values. And those values may represent things like the colors, for example. And so 2-dimensional arrays are really easy to store and compute. And so how would we even think about having a data structure that just stored the individual pixels in here, right? Like it would have to be some sort of list and then locations, and it would be annoying. So we just store the whole rectangle, and images are stored as rectangles in pretty much any system that I've ever seen. So because of that, these rectangular images make a natural fit for a rectangular bounding box. And so why not just use the bounding box as the image, right? So if the image is a particular size, that typically denotes what we want to display, and so why not just use the bounding box as the size of the image? So usually the bounding box will be the smallest rectangle that fits the sprite. So we can use the texture size as the bounding box size. However, sometimes that works, and sometimes that doesn't work. So let's look at some cases where that maybe does work. Well, if we have constructed our assets in the game to be rectangles, and to not have any like real, this is exactly a rectangle. So if we use the exact rectangle as the bounding box, that's probably fine, right? So all these things up here. But then Mario, okay, we run into that thing where, okay, it's not exactly a rectangle, but Mario's pretty rectangular if you actually look at the sprite, right? So, okay, we're going to use it for this. And you can see here for a pipe, there's a little bit of white space, but like really, come on, that doesn't really matter that much. So using rectangles is usually pretty fine. However, we may not always want to use the size of the texture. And I alluded to this a little bit in a lecture a couple of lectures ago. But typically, we want to use the same image size for all of our textures for a given entity, right? So for example, these are all of the frames of animation of Mega Man. I think the only thing I maybe don't have here is like if Mega Man does something when he shoots, okay? So here you can see that sometimes Mega Man is quite taller or wider than in other frames, right? Like here Mega Man is pretty thin in the X direction, and here Mega Man is quite tall in the Y direction. And so what we do is, if these are frames of animation, they need to be in the same size image, right? So what we do is we say, okay, let's not take the bounding rectangle necessarily to be the same size as the image. So in the actual game of Mega Man, this is sort of what the textures look like. They are a bit bigger than Mega Man in order to hold things like this. And then we decide, okay, what is the bounding rectangle within that texture that we actually want to make the thing that collides, right? So if you do jump onto a platform, you can see, or if you're underneath a platform and you jump up into it, you can see that a few pixels of Mega Man's head actually does like overlap with the tile above. And so that's, my head is not going to be able to overlap with a tile in real life, but it's fine for the purposes of most games. So over here you can see that we're going to choose the same bounding box size even though the size of our sprite may change within it. And that's just an abstraction that we make to make things much easier. However, in Super Mario Brothers, these are the actual bounding boxes of the sprites that you see in the game. And so if you've ever watched like a speed run of Super Mario Brothers, if you haven't, you should. They're amazing. But over here, for example, you may see in the speed run Mario jumping like through piranha plants. They come up through the pipes and they just run and they jump, and it looks like Mario's legs are like being eaten by the piranha plant. But the reason that can happen is because none of that part of this sprite is actually a collision box, right? So the collision box of the piranha plant is just this. And the collision box of like the whole fire sprite is just this thing right here. And also you may see like, okay, like for example, the squids, typically they swim below the squid, and you can see like a tall Mario actually going through like Mario's head right here. There's no collision in the hat, so the hat can pass through anything, and there's no collision with the tentacles, and so the hat can easily pass through the tentacles. And you're like, why didn't Mario die there? And that's the reason for that. And you can get some very interesting things that happen because of this. So like if you had, you know, pixel perfect alignment in your game, you can actually see situations where Mario should probably not survive, but ends up surviving because of things like this. But how do we actually detect the rectangle collisions? Well, in the arbitrary case, rectangles in a 2D plane can take any orientation, right? As long as all four corners form 90-degree angles, then that's the definition of a rectangle. And so detecting the intersections of arbitrary rectangles, it can be a little bit slow. Slow in comparison to what we will be doing. But if we, you know, had to detect arbitrarily rotated rectangles, the only way to do that would be to say something like, okay, for each of these line segments, see if they intersect with any of these line segments, right? And so for 4 of these line segments, okay, that's 16 calculations, 16 line segment calculations, and then within a line segment calculation, which we'll be talking about in a future lecture, there may be half a dozen or more actual mathematical calculations. So we may have to do hundreds of things to just detect if these two rectangles are overlapping, which is not something that we would want to do. So typically what we do is we're just going to say, okay, we're going to take our bounding boxes and we're going to align them to the axis. So the top and bottom and the sides of the rectangles are going to be parallel or perpendicular, however you look at it, with the axis, the x and y axis. So by aligning our rectangles with the xy axis, we're trading this like ability to have arbitrarily rotated things for a much faster intersection and collision detection test, okay? And so axis-aligned bounding boxes, that's AABB. So if you've ever seen that before, now you know what it is. So let's talk about some of the math of AABB calculations. And so the simplest thing that we could do with an AABB is to see if a single point is inside it, right? So if I have a rectangle, there are a couple of ways to specify rectangles, and depending on the graphics library or the math library that you're using, rectangles can be represented in one of 2 main ways, or both. But one of the ways is to specify the top left corner and the bottom right corner. Another way to do it is to specify the top left corner and then the width and the height, right? But you do need 4 values to specify a rectangle. You need to specify some point of some corner of the rectangle, and then, you know, tell your programmer that that is like the top left, for example. And then you need some way of representing how big the rectangle is, and so you either do that by having also storing the bottom right or the width and the height. And then we have some other point over here. Now, a point is a infinitesimally small thing, but I'm representing it here by a circle, just so you can see it. And so this point is going to have coordinates point x1 and point y1. So how would we detect if this point is inside the rectangle? Well, I'm sure that you could all very easily write this algorithm. But if we are taking 0, 0 as the top left corner, and so x increases to the right and y increases down, just like SFML does, then, okay, essentially this point is in the corner if it's within the rectangle. So how do we say within the rectangle? Well, px is going to have to be to the right of the left wall. That's what this is. So if px is greater than x1, it's going to have to be to the left of the right wall. And you can see where this is going. It's going to have to be above the top, or below the bottom, and above the top, right? So 4 different calculations here. And this, if all of these are true, then that point is within that rectangle. If we were to look at this from the point of view of the other way of representing a rectangle, which is xy as the top left corner and width height, then P would be inside if, well, okay, it's still to the right of the left, but now instead of having x1 and x2, we have to actually add the width to x. So that's what x1 would have been before. And okay, we have to be below the top and we have to be above the bottom. So that's a relatively simple calculation. So the next thing to do is to determine if 2 axis-aligned bounding boxes intersect. So this is a Boolean check to say if two of these things intersect. So you might say, okay, well, I just learned 2 ways of possibly doing this. One would be to say, all 16 checks to see if any line segment of one intersects with any line segment of another, right? So I could take all of these lines here and try and intersect them with all of these lines here. But what's wrong with that algorithm if we decided to implement it? Can anyone see a case where that may not work?
One rectangle is entirely contained in another.
Exactly, right? So we can't just check to see if the line segments intersect because, as you said, if this red rectangle was entirely within the other one, then none of the line segments would intersect. And so that algorithm doesn't work, so we can't use that one. We could, however, do what we just did with a point being inside the rectangle, right? So we could check if, for example, all of these red corners were inside the green one. So that's one thing we could do. But that, again, that is 4 checks, 4 if statements per point, and 4 points. So that's like 16 if statements to see if this rectangle is within another rectangle. Let's see if we can do a little bit better. So before we talk about entire rectangle overlaps, let me introduce this other concept, and that is the concept of horizontal overlap. Now, if you Google AABB horizontal overlap, this is just something that I named it, so you may not actually get this exact method that I'm using, but it's the most efficient one that I could find. So I'm going to define horizontal overlap as occurring if the top of each box is higher than the bottom of the other box. Essentially, it means, can we draw a horizontal line that intersects with both boxes? Right? So yes, I could draw a line across right here that intersects with both boxes. That's the concept of horizontal overlap. So if I have 2 rectangles, how would I determine if horizontal overlap is occurring? So it says if the top of each box is higher than the bottom of the other one. So if this is above this, and this is above this. And that's not super intuitive at first, but if you think about it, then that's provably true. That is how there would be a horizontal overlap. So how would we detect it? So it means that the top of this, y1, has to be less than y2 plus h2. So it has to be above this one. So because y is flipped, above means less than. And also, y2 has to be less than y1, or sorry, y2, the other top, has to be less than y1 plus h1 down here. So there is horizontal overlap if this is true. Okay. The opposite of that would be vertical overlap. So vertical overlap means, can I draw a vertical line that intersects both rectangles? And I guess you could say, okay, maybe this is horizontal overlap and the other one is vertical overlap. It depends on how you define it, right? These are just how I've defined it. So very, very similar to the other one, we have to check if the left of this one is to the left of this, and if the left of this one is to the left of this. Okay? So that's just 2 checks. So if x1 is less than x2 plus plus w2, and if x2 is less than x1 plus w1. So hopefully you can see where I'm going with this, is that if there is horizontal and vertical overlap, then we have an AABB intersection. And so axis-aligned bounding boxes intersect if they are horizontally overlapped and vertically overlapped. And so that's just 4 if statements. Okay, so that's much more efficient than the 16 of checking all the points. And the line segment one wouldn't even work, so we can't use that one. And so this is the most efficient way that I've found of doing this. And so this will tell us if the first thing and the second thing and the third thing and the fourth thing. If any of those are not true, then there is not a horizontal overlap. Or there is not an overlap of the two AABBs. So this tells us if the two things intersect, but it doesn't tell us by how much. So I want to know the area of this. And I'm sure you could all figure that out, but let's do it anyway. And what we're going to do in our game engine to make some things a little bit easier for us is instead of using x1, y1 as the top left of a rectangle, we are going to be using it as the center of a rectangle. And that affords us some kind of nice mathematics at the expense of this little bit of extra mental load, right? Of now I have x1, y1 being the center of a rectangle. So let's look at the math now with respect to the center of a rectangle. So how do I calculate the overlapping area for a center-positioned axis-aligned bounding box? And this is going to be crucial to assignment 3 because we're making a Mario clone and we want to be able to intersect bounding boxes. So if we have a rectangle, which is now being specified by xy as the midpoint, width as the w as the width, and h as the height. Well, inside our transform, or inside our entity, we are going to have two components which we're going to deal with to do this. So one of them is the transform. So the transform is going to store the position. It's also going to store the velocity, scale, whatever, but we're really interested in the xy position here. And we also have a bounding box component. And the bounding box is going to have a given size. And what we're going to do is, because we're talking about the center of a rectangle, I am also going to be storing a value which is half the size. Now, Dave, why are you storing half size? Isn't that just extra memory? Yes, but that little bit of extra memory is going to save us dividing by 2 everywhere, right? So we're going to be doing a lot of dividing by 2, so let's just store the result of taking the size and dividing it by 2. And so this half size is half the width and half the height. Okie doke. So let's keep going. Where am I going with this? So if I want to tell if there is this horizontal overlap between two things, then I'm going to do the following calculation. So I'm going to take dx, which is the distance between the centers in the x-axis, and that is just x2 minus x1, and take the absolute value of that. And the reason we take the absolute value is because you never know. x2 might be to the left, it might be to the right, we're not sure. So the distance between them is just the absolute value of the difference. Now if I have width 1 over 2, so this is half the width of the first one and half the width of the second one, then I have a situation that looks like this if I delete the rest. Okay? So if I have a situation like this, there was no overlap here. Right? In a situation where there would be overlap, it would look like this. Right? So there's no overlap here. There is overlap here. So this is very similar to how we detected the collisions with the circles. Right? The radius there was half the diameter, and now we're also storing half the width or half the diameter of a rectangle, if you want to look at it like that. So there is overlap in the x direction. Saying x overlap is a lot better than saying horizontal overlap, probably. If width 2 over 2 plus width 1 over 2 minus x, if we take this and it's positive, then there's an x overlap. So it means that if the sum of this line and this line is greater than this line, then there's an overlap. So that's a pretty simple calculation. Let's do it in the opposite direction. So we have these two rectangles, and we have the difference in the y positions of their centers. That is just the absolute value of the difference of the y positions. Then we have half the height and of each. So again, in this case, there would be no overlap vertically. In this case, there would be an overlap. Okay? So there's an overlap if the sum of half the sizes is greater than the distance. So if this value is positive, then there's a y overlap. So let's combine all of those together. So we have two of our rectangles. So we're going to store this delta, which is the delta or the distance between the centers of the two rectangles in the x and the y. So in the x, that's just the absolute value of the difference of the x's. And then in the y, it's the absolute value of the difference of the y's. And then we're going to take OX. This is the overlap x. That's what O stands for, which is the formula we just said. So you sum up the half widths, and then you subtract the distance. That is the overlap x. And then you have overlap y, which is the sum of the half heights, and you subtract the difference in the y's. And then the overlap rectangle is going to have the size of OX, OY. And so, how will I know if there's actually a collision by looking at OX and OY? Yep.
If OX and OY are negative, then there is no collision, and if they're positive, then there is.
It's a little bit stronger than that. So if they're positive, there is, but if either of them are negative, then there isn't, right? So if either of those are negative, there's no overlap. So it means that, hey, there's a negative overlap, which means they're separated, right? And whether or not you count 0 as a collision is up to you in your game engine. Okay, so if you want to be sure that there is an actual overlap that's greater than 0 in order to resolve something, that's up to you. But you can use this OX and OY to then resolve your collisions somehow. And so let's talk about that. So now that we've actually detected the axis-aligned bounding box collision, what do we do? So the resolution of the collisions is going to depend entirely on the physics and the gameplay of your system. So I'm going to show you one way of doing it here that we're going to use for assignment 3, but this way of doing it, you can still use the mathematics of all of this in whatever game you want, but if you wanted a different thing to happen when two things collide, then of course you have to do your own collision resolution system. This is going to be a very basic case for like Super Mario World. But if you wanted, something to bounce off of something else, then you start having to change velocities, et cetera, et cetera. So for example, if the player collides with a tile, let's talk about like real world physics. So real world physics would be something like if I have two pieces of like diamond, right, that can't deform and they can't bend each other. And so I have one piece here, or let's just take the table. Right? So I have a table. If I have this, whoever's water bottle this is, if I try and move downwards, even if I'm overlapping the air, it's going to collide with that, right? And it can't move through. If I'm going from the side, it's going to collide with that. Now, in a game like Mario 64 or something, if you come from the side, and maybe this is a stair, you actually want to be able to run up the stairs. So if you're coming from the side and you collide by only a little bit, maybe you actually do want to let it go up. Right? But we're just going to bang off the side in this case. So you can do all sorts of stuff with the same math, but how you actually resolve the collision is going to be up to you. Well, not up to you in assignment 3, but up to you if you made your own game. So let's have a look at a collision. We've got two rectangles here. This is on frame 1 of the game. So just remember that each frame of the game involves two steps. One is the actual updating of the positions. The second is the rendering. So we do the physics and the math, and then we do the rendering. So frame 1 here means the actual like rendering of it. So this is what it looks like to the user. So it looks like this on frame 1. Okay, so the green rectangle is going to be moving to the left, then to the left, then to the left, and now we have entered frame 5. We haven't rendered it yet. This is what it looks like now to the game's physics, right? So we've detected this collision. We have this overlap rectangle where they're both non-negative. So we have an overlap in the x and the overlap in the y. So one thing that we could say, okay, let's do the simplest possible case of collision resolution, where I have an overlap. And so let's move one of the rectangles by the overlap. So if I just took the green one and added the overlap as the position, then I would push it out like that. So I've detected by how much they overlapped. And so I'm just going to take the x component of the green one and push it back out. So you can see here that each of these I was going up by 1 frame, but here it says frame 5 and frame 5. This part of frame 5 happens, but the user doesn't see it. All the user sees is this, the result of the collision. But the collision has happened in our actual game engine, and we need to deal with it. So the idea here is to hide that detail from the user. We don't want to render that frame. We fix the collision before we render it. And then on frame 6, well, if you've still got the speed going, right, if you just have a velocity, it's going to move into the shape again, and we have to push it out again. And then it goes in again and pushes it out again. And so every frame, you actually do have this happening, where it's like in, out, in, out, in, out, but the user just sees this. They don't see that. Okay? And one of the things that can happen, and probably will happen at some point in your game, is that you're going to have gravity acting on something. So what does gravity do? Well, if we have a fixed velocity, right, let's say this is the game, so this is going to be in the table at some point, and it's going to be pushed back out. And it's in the table, then it's pushed back out. So you're just seeing this, right? You don't notice it. But if you have gravity, gravity's saying we're increasing our speed moving downward on every frame. So gravity is going to push it down by 1 millimeter at first, and then we'll push it back up. But now it'll go down 2, then we'll push it back up. Now it might go down 3, and at some point, it's going to push it, after a few frames, through the table. Right? So on one frame it will be here, on the next frame it'll be here, and what can you do? Right? Well, one of the things you can do is if you detect a collision, reset the velocity back to 0. Right? So that means that every frame velocity has to start acting again, or gravity has to start acting again on it rather than continuing that speed. And that bug is why you can clip through most walls in most video games. Right? So Mario 64, if you've ever watched any speed runs of Mario 64, where they clip through walls or do BLJs or any of these tricks, it's because the developers capped the forward motion, but not the backward motion. So if you can figure out a way to go faster in reverse, there's no limit to that. So eventually you build up enough speed to just go through the wall. Okay. But this is kind of the easy case where it is just, it's just going in one direction. What if we had something like this? What do we do now? Right? In this case where we're overlapping at the corner. Well, maybe if I just added the overlap, then I would get this. Moving to the left, and then I'd see that. And that looks very computery, right? Like that doesn't look like something that would happen in real life. That looks like bad physics. So we have options here. Option number 1 might be to push it up here. But the problem here is that in the physical real world, that can't happen. Right? It's saying, I'm going to have this overlap, but then I'm just going to push it up. That's the example I gave there. If it came from the right, then maybe it should collide with the side of the wall and not be pushed to the top. So maybe it should look like, did I just show that? I think good. Yeah, so it would look like this in this case. Maybe if I have stairs and I wanted to do that, that's good, but not for our assignment here. So the second one might be to just push it out to the side, right? So we literally have 2 boxes colliding and they just stop there. So this is probably the best actual real-world physics for our game. So it would look like this, and it would just stop there, right? So it's pretty intuitive. So in order to do this resolution, how do I detect whether or not something was maybe coming from the right or from the left or from the top or from the bottom? Because, for example, in Super Mario Brothers, if you hit a brick from the bottom, as Big Mario, it gets destroyed. But if you hit a brick from the top, you just stand on it. Right? So detecting if it's coming from the top or the bottom or left or right is important. So when you detect collisions in a game, it will first happen on like a specific frame. So the collision happened on frame like 17. It didn't happen on frame 16, but then it did on 17. So by definition, the frame before the collision was detected there will be no collision. So there was no collision on one frame, and then there is a collision on the next frame. So we could try to use the overlap to maybe detect which direction the movement came from. So if we're trying to detect if we came from the right or from the top or whatever, let's try and use that box, the overlap, to detect that. So for example, which direction did the green rectangle come from? The right? Okay, I guess go. Both of you said right. One said right and one said top, I think. Well, we don't know. It could be either one. So if it was moving really fast, it could have come from the top. If it was moving slower, it could have come from the right. And so it could have come from the y direction if it was going fast. It could have come from the x direction if it was going slow. So what we can do is let's incorporate some information from the previous frame to detect where it was coming from. So we can't just use the overlap to detect which direction it came from. We've got to use some other information. And so it's what I'm going to call the previous overlap. So at any given time, we're going to store the overlap on this frame, and we're also going to look at the overlap from the previous frame. If the previous frame's overlap y is greater than 0, so if I can draw a line between two of them, then the movement came from the side, right? Because if we're overlapping in the y, then we couldn't have come from the y. That's just, hopefully that's obvious to you. And so if this is true, then we're going to resolve the collision by pushing in the x direction. So if we detect that on one frame we have a y overlap, but no x overlap, then on another frame we do have both. We know that that came from the x direction. So we can push it in the x direction to resolve that. Similarly, if on the previous frame we have an overlap in the x direction but not the y, then we know the movement came from the y, and so we can push it up. And so this is going to afford us the resolution that we actually want in assignment 3. However, so a collision came from, this is telling you if it's x or y collision. It still doesn't tell you top or bottom. So top or bottom detection is a collision came from the top if the previous overlap had an x greater than 0 and the y value is higher, meaning less in our case. So that's how you know it's the top. And a collision came from the bottom if the previous overlap was greater than 0, or the x overlap was greater than 0 and its y is lower. So I can similarly do the left and the right detection by if it's a horizontal movement and it's greater than, then it's from the bottom. If it's less than, it's from the top. Oh, sorry. And the other way, if the x is less than, then it came from the left. If the x is greater than, then it came from the right. But the ones who are paying attention have noticed that there's still another case. What if the previous frame had no overlap? So it came in from a diagonal, right? Well, this is just a tricky case. And what you have to do is you must decide somehow on some sort of priority, right? So you must decide how to resolve this collision based on the previous position and or overlap size. So for example, you might say, okay, I want to resolve all diagonal collisions by pushing it up. Or maybe I push it up by the entire overlap so it lands right on the corner. Or maybe if the x value is greater than the y value, then it collides with the side. If the y value collides with the top, or whatever. But you have to decide on something for this. And you're not alone in this frustration, because this happens in games, right? So these are tile collisions that are happening. Mario comes in from the corner and is able to very briefly, for one frame. Now, Mario does its collisions after the rendering, so you're actually able to stand on that thing. So what's happening here is Mario is in this state for one frame, and if you press the jump button on that exact frame, you can wall jump in the original Super Mario Brothers. And so now we start to see how these glitches are happening, or glitches or features depending on how you look at it in older video games. There may be a tricky case here. What if an entity is going to overlap with multiple entities? So if we have a wall made out of tiles, what do we do now, right? Well, it turns out that if we follow what I was just saying, then this will properly push it out to the side, right? But the order of collision checks is now going to matter, right? So if we collide with the top brick first versus the bottom brick first, maybe we would have a different outcome. Turns out that all of these are all being collided from the right, so we would have the same behavior. So stacks of stuff usually isn't a problem, but if we have diagonals and things coming in, and in one brick it was coming from the left, but maybe in another it was coming from the top, now we may have something that there's always little tricky cases like this that you have to deal with. And so the previous overlap method discussed usually resolves this case, but using the previous position only doesn't. So it usually resolves it, but not all the time. And so this can lead to things like this, the original Super Mario Brothers. Now this is a gross oversimplification of what's actually going on here. But when you collide with multiple tiles, one is pushing down, there's like an escape velocity based on the way Mario is facing, and I can link videos of exactly what's happening here. But this is a possible thing that can happen if you'd said, okay, for example, back here, maybe we do the resolution by just pushing Mario up, and then he's still capable of moving to the left, right, if we didn't do them in the correct order. So things can happen, but I've never seen that happen in our game using the correct physics. So just an important note is that all the collision resolution that we talked about is for the simple case of avoiding overlap. So it's useful for like walking on tiles, if you have a ground tile or a question mark block or whatever. If a bullet hits an entity, you can destroy it if you know that they're overlapping. But there are many other kinds of collisions in arbitrary games that you might have. So, for example, if two things are moving toward each other in an actual physics simulator, they're going to have mass and orientation. And so, for example, if this is a really heavy like anvil falling, then it's not just going to stop. It's obviously going to push the other thing. But we're not getting that into detail. So we could take the whole class to do physics simulations if we wanted to, but we're not going to do that. A quick side note is that Super Mario Brothers collisions operate differently than what we presented. And so let's detect, for example, if Mario is jumping on top of an enemy, right? So you may say, okay, if there's a collision in both the X and the Y, then there's a collision. And if it came, if it's landing on the top of the other entity and there was no other previous overlap, then we would say, okay, now it's landing on the top of the entity. But in Mario Brothers, the same AABB is used to do the overlap detection, but the only thing that the game checks is if there's a collision and if Mario is moving down. So you can actually collide with an enemy. So for example, in this case, I didn't draw a bounding box, but Mario is not entirely on top of this Goomba. But if there is a collision and Mario is currently falling, doesn't matter. He can hit the side of an enemy. So if you've ever seen Mario, like a Mario speedrun where they do something like this, especially like Koopas, flying Koopas that are moving up and down, and then Mario just comes along and like jumps off the bottom of the Koopa, it's because he was moving downwards and there was a collision. So all Mario Brothers checks is if Mario is moving down. And then if Mario is moving up, for example, over here, then Mario would die on this collision or become small or whatever. So that's just a quick note that, games do it differently, and this was just to save on computation. So that the whole process that we talked about of all this collision detection and resolution with, getting the overlap box and stuff, that's not being done in Super Mario Brothers. There's a quicker system being used that is less accurate, and you can get these side effects of being able to move through walls and stuff because of that. So this video, has anyone seen this video? Does anyone here watch like speed running of like Super Mario and stuff? Okay, I live for that stuff. I watch way too much of it. I can't imagine how much research I'd actually get done if I stopped watching YouTube. But there's a few videos here that you don't have to watch, but if you're ever like, eating dinner and you want to put on a video, these are insanely entertaining. and they will give you some appreciation for the programming of these games and for the programming of assignment 3, I think. So this first one is, so Bismuth is a YouTuber who took the Super Mario Bros. 1 speedrun, which involves many different glitches, probably a dozen different glitches, and then explains like the mathematics of all of them in a way that like probably took him like 2 months to make that video, right? I can't give you the same quality video as this person explaining those physics. This next one by Pan and Coke, so he's very famous for doing the 0 A button challenge in Super Mario 64. So he's trying to beat Super Mario 64 and collect all the stars by not jumping. And so by using various glitches in that game to not jump to get all the stars. And they can collect 120 stars in something like 10 A presses now or something. It's insane. So this, Walls, Floors, and Ceilings, explains how Super Mario 64, for the N64, the first 3D Mario game, handled walls, floors, and ceilings. So you can probably tell that 3D collisions are much more expensive than 2D collisions, right? And the N64 wasn't that powerful in comparison to modern day computers. So we could do the 3D equivalent of running an entire physics simulation in our modern day computers, or even on our phone, for God's sake. But back in the day, you had to make some like weird things happen in order to get all this physics running in real time on a slower processor. And so this goes over how Super Mario 64 differentiated between wall behavior, floor behavior, ceiling behavior, can you grab or double jump here, like all sorts of things. And it has to do with the angles of walls, and like in Tick-Tock Clock, there's spinning platforms, and these things are interpreted as a floor or a ceiling or a wall, dependent on the current angle of rotation, and it changes in real time, and it's really cool. And then there's this video, which is like, has anyone seen the meme of like the parallel universes when explaining things in video games? So a couple people. So it turns out in a Mario 64, there's like, if you can get Mario moving fast enough to wrap around the integers, then you can land in a parallel universe where there are no graphics, but there's still the geometry of the level, but there's no graphics and there's no moving entities. So like the integer space that they use to store the geometry of the level is different from the integer space of the entities in the level. And so they get like a trillion speed with a task, so they're using a computer to program all this. They go to one of these parallel universes, and now you can get past that door that used to be there or whatever, right? So it's a very, very entertaining video. I'd say all these together are like more than an hour of content. Like, I wish I could put this on an exam to force you to watch it, but I mean, they're really entertaining, and I think you'll enjoy them, so I just put those there. And it's great. We get to end early today. But that's the collisions. That's what we'll need to know for assignment 3. And just to be double sure for anyone who wasn't here last time or doesn't read D2L or doesn't watch the lectures, don't come to class next week because I won't be here.